To the lecture for chapter 31. Here we're going to talk about the light quanta. Okay, so if we're going to be talking about quanta, that means we're going to be talking about quantum physics, which is just the physics of little indivisible pieces of things. That's what a quanta is. A quanta is the smallest piece of something. A quanta of light is the smallest piece of light, which means that light comes in pieces, but we'll talk about more of that in just a minute. Okay, so we'll talk about the birth of quantum theory. We'll talk about, quantization and Planck's constant, kind of like where the whole impetus behind the idea of quantizing things comes from. The famous experiment that proved that light comes in quanta, which is to say it comes in particles, which is the photoelectric effect, experiment by Einstein. The wave-particle duality, a kind of return to the double slit experiment, which we've talked about actually when we talked about the wave nature of light and the interference. But we're going to bring it back up because that's going to lead us to talking about the idea of the duality. So these are very much interconnected ideas. The duality of light being that it's both a wave and a particle. We'll then talk about particles as waves, which is electron diffraction. The uncertainty principle, which gets into one of the consequences of having quanta. And then finally, complementarity, okay? Which is how the idea of quantum mechanics fits in with other theories of physics. Okay, so I've hinted a lot at the idea that light is a particle, and certain ideas I mentioned in previous chapters being like, oh, that's a quantum mechanical idea. We'll talk about that later. So we are finally talking about that. We're going to actually talk more about the quantum mechanics of the atom in the next chapter, but we're definitely laying the groundwork for that here. So let's talk about the birth of quantum theory. So there has been a long historical debate about the nature of light. All right. Some believe it to be particle-like, others believe it to be wave-like. So that was the background going into this idea of accepting that it's both. But let's get there. Young's double-slit experiment in 1801, to get some kind of historical perspective here, proved the light was a wave, almost seeming like the debate was over. However, Max Planck in 1900, so about a century later, hypothesized that radiant energy was emitted in discrete bundles. Okay, that's different. Each of which was called a quantum. Now, he was specifically thinking about heat energy, but obviously heat energy in a vacuum is light. There's no other way to propagate heat. Okay, that's how we spread energy. So how do you reconcile these two ideas made, or experiments really, designed a century apart? Well, let's see, okay? So what did Planck do in 1900 with this idea of hypothesizing the idea of the quanta? Well, quantum physics states that in the microworld of the atom, the amount of energy in any system is quantized. Not all values of energy are possible. It's like having steps versus a ramp. On a ramp, you can stop at any height. On a staircase with steps, you can only stop at the particular heights that the steps allow you to. That's the idea between a quantized method of going up versus a continuous method of going up. The ramp being continuous, the steps being quantized. That's exactly what we're talking about here. All right, so example, the energy in a beam of laser light, which is a whole number multiple of a single lowest value of energy, 1 quantum. The quanta of light and of electromagnetic radiation in general are the photons. Okay, that is the quantum of light, which is the particle. Okay, so we could say that the photon is the particle of light. It's also the quantum because they're interchangeable terms. It's the smallest piece. All right, and the energy of 1 quanta of light, 1 photon, is equal to this formula right here. E equals hf. All right, that's the energy of 1 photon. Okay, photon is energy times frequency. Okay, now we've already proposed that because we talked about excitation levels in an atom, and that basically the idea that, this should be an H, but the idea that E equaling Planck's constant, H, making this as obvious as I can there, H times frequency, that energy had to be equal to the energy difference of the electron excitation levels. All right, so we've seen it once before. Okay, so quantization is the idea that the natural world is granular rather than smoothly continuous, and the quantum is any elemental particle that makes up matter or carries energy. Okay, so that's just to summarize the terms here. That's what quantum is all about, breaking things into discrete, indivisible little pieces. Okay. So how does this lead to the photoelectric effect? Well, the photoelectric effect is a model for how matter radiates. It was hypothesized by Max Planck, and it supposed the idea that warm bodies emit radiant energy in individual bundles, and the energy in each quantum is proportional to the frequency of the radiation. Okay, so there's the formula again. The energy of individual particles. All right, and light shining on a negatively charged photosensitive metal surface liberates electrons. Electrons are also particles. So you have light shining on a surface and then interacting with the particles within that surface, the electrons in the metal. Okay? All right? Because metals are known for having lots of easily freed electrons. So the same electrons that are easily moved around in the metal that makes it a conductor. The liberated electrons are attracted to the positive plate and produce a measurable current. If we instead change this plate, or charge, this plate with just enough negative charge that it repels electrons, the current can be stopped. All right? So the idea is that naturally electrons are going to get attracted to the positive plate, okay? But if we make that plate less positive, then the electrons won't make it, okay? Because they have to have a certain amount of energy to jump the gap, okay? And if there's not enough energy to jump the gap, then they won't, okay? Which will tell us how much energy they had in the first place, how much energy the electrons had when they were freed from the metal. So then we can easily then calculate the energies of the ejected electrons from the measured potential difference between the plates. So it's a very practical experiment. It's quite easy to carry out. It can be done in a teaching lab, in a college level teaching lab, very easily. Just all we need is a certain type of surface and a certain type of light source, but easily come by, just as some sort of metal surface, a basic, circuit like this, and then some light source like a laser or a diode, so we can control the frequency. Okay? So the idea, okay, we call it the photoelectric effect because the photo is the idea that the photons, right? We're shining light on a metal and we're getting electrons. So that's where the light is the photo part and the electric is the freed electrons. Okay, so the name makes sense. Photoelectric effect, light freeing electrons. So light ejects electrons. Okay, that makes sense. And that, by the way, could happen whether the light was a wave or a particle. Because energy certainly can, we could heat up the metal and essentially boil away the electrons. So is that what's happening? Well, there's a way to find out. So more light ejects more electrons with the same kinetic energy. So if you increase the intensity, or just in this case, it's the number of light sources, which is effectively increasing the intensity, then there's more electrons being freed. That makes sense. Again, that would happen for a wave as well. All right. Now this part though is strange. Low frequency light does not eject any electrons. Now it depends on the metal what the frequency is, but every metal has a certain cutoff frequency where there's just no electrons being ejected. Okay, so that's kind of strange because if light was a wave, then certainly the lower frequency light would have longer wavelength, all right? So it could be lower, so there could be less energy, but over time it should still be able to heat up the metal, right? The metal should still be able to absorb that energy over time, continue to heat up, the electrons would continue to get that heat in the form of random kinetic energy. Some of them eventually would have so much random kinetic energy, they'd be able to be freed from basically the energy that held them in the metal. What's what we call the binding energy in the metal. It's actually called the binding energy. So, but that's not what's happening. Low frequency, long wavelength light, okay, is just not freeing any electrons. There's a stark threshold under which no electrons are liberated, okay? A stark, defined frequency threshold. High frequency light does eject electrons, even if it's low. So even if we make this beam 1/3 as bright, if we drastically decrease the intensity of the beam, but keep the frequency high, we'll still free electrons. So you see that the intensity is completely non-consequential of whether electrons get freed or not. Now, once electrons are getting freed, then more intensity means more electrons. But the cutoff is entirely frequency dependent and is not intensity dependent at all. So this leads us to a very interesting conclusion. So Einstein's view of light was this: as a stream of particles, bundles of energy, the photons interact with matter one at a time. So the high energy photons dislodge electrons from certain metals. Because if each particle of light is behaving like a particle, then it makes sense that the low frequency, low energy photons just won't have enough energy to collide with the electrons and actually bounce them out. All right? Again, if it was a wave, then it wouldn't be like a collision. It would just be gradual heating of the metal. But that would free electrons. All right? So this right here, this behavior of having a threshold is pointing to particle behavior. So, in the photoelectric effect, the brighter the illuminating light on the photosensitive surface, the greater it's the number, okay? Because essentially it means more photons, more electrons. See, more photons means more electrons. Now again, you could explain the greater number of freed electrons with a wave as well. But once you have the idea that only this behavior can be explained by the particle, then this behavior here is consistent with it. The greater intensity resulting in greater numbers of electrons. In the photoelectric effect, the higher the frequency of the illuminating light on the photosensitive surface, the greater the what? The higher the frequency. What happens in that case? Think about it. That means higher frequency, think particles. That means each individual particle has more energy. When it collides like a billiard ball, if you will, with an electron, what would happen to an electron if the photon has more energy? Okay? Well, it would get bounced away faster. Now notice I'm saying the photon has more energy, not that it's moving faster. Be careful to not say that, because if it really was a billiard ball, you'd be like, oh, fast, the faster impact, means, faster, like ricochet. But of course the photons aren't moving faster, they just have more energy. All photons move at the same speed. Please remember that, okay? So, this leads to the wave-particle duality. A photon behaves as a particle when emitted by an atom or absorbed by a photographic film or the detector, like the photosensitive metal. But it behaves as a wave in traveling from a source to the place where it is detected. In a vacuum, it only displays its wave-like behavior. In this sense, light can be both a wave and a particle, depending on what it's interacting with. Okay? So here is a great example of a wave-particle duality of light. We have an image built up by individual photons, one photon at a time. And we can clearly see that the behavior is exactly, it's building up like individual collisions, right? One little dot, one dot building on top of another. Okay, so this is sending a bit of data one photon at a time until the total amount of data is revealed. But here's the thing. That's the case. If you can build up something one photon at a time, then it might make you think, okay, well then the photon is it, right? We don't really need the wave, right? Why do we have to say it behaves like a wave when it moves to a vacuum if you got the photoelectric effect, which is clearly particle-like behavior, you have an image here which is being built up one photon at a time? Well, that's because there's still definitive evidence that it's a wave. In fact, you can take a single photon, like the ones that are making individual collisions here on the photographic paper. You can take one of those individual photons and shoot it or direct it through a slit. All right? So imagine the double slit experiment again. This is a famous experiment that proved light was a wave back in 1801. Okay? But now let's imagine with a single photon, a particle of light. Well, if we send that light through, that particle of light will actually interfere with itself. And it will have the same likelihood of arriving at a certain location on the screen as the relative likelihood of the intensity shown over here as a graph. In other words, the photon will be much more likely to arrive at any of the spots which show up as a bright spot, and very unlikely to show up as one of the spots that show up as a dark spot, and some in-between likelihood to show up in between. But its actual location is random. Okay? Because it has to be. Because only can you have random behavior like that to explain light being both a particle and a wave. It must be inherently uncertain because it must behave like a wave. It must interfere with itself. Well, interfering with yourself, a strange idea, right? And kind of a limited way to explain what's going on, but hopefully a good analogy. that means that there's an inherent uncertainty in the wave-particle duality of light. So then imagine, right, then if you continue to send photons, billions of them, then they'll continue to land in the most likely places, and the overall effect will be the result of bright fringes and dark fringes, okay? And what we call an interference pattern, all right, which we would see with any wave, like a sound wave or an ocean wave, okay? But it's still happening for individual photons, okay? So this elaborates on the idea a bit. I'm just going to read through this. Suppose we dim our light source so that in effect only one photon at a time reaches the barrier with the thin slits. If the film behind the barrier is exposed to the light for a very short time, the film gets exposed as shown below, just a few individual photons. Each spot represents the place where the film has been exposed by a photon. If the light is allowed to expose the film for a longer time, a pattern of fringes begin to emerge. The photons start showing up the most likely spots, leaving the spots where wave interference tells us that we must have total destructive interference. Indeed, no photons are going to show up there because it's very unlikely. If we cover one slit so the photons strike the photographic film can pass only through a single slit, the tiny spots in the film accumulate to form a single slit diffraction pattern. So even in a single slit, we still have the diffraction behavior. We still have a spreading out of the photon. It literally is becoming uncertain. Aha. We find that the photons hit the film at places they would hit if both slits were open. Okay. So how do photons traveling through one slit know that the other slit is open and avoid certain regions, proceeding only to areas that will ultimately fill to form an interference pattern? Well, each single photon has wave properties as well as particle properties. The photon displays different aspects at different times. The photon behaves as a particle when it is being emitted by an atom or absorbed by a photographic paper. All right? So when the photon strikes the film as a particle, that's great, but it travels to its position as a wave that interferes constructively. Okay? So we have the photon, which is a particle, we now understand, right? They sent me really a century later, right, in terms of the history of physics. But now we understand that light is both a particle and a wave. So that begs the question, are there other examples of particles that are waves? And indeed there are. Electrons themselves are also waves. Okay? So we find that electrons, definitely a particle, okay, even with a known mass, unlike the photon, which is definitively massless, well, we find that it can also interfere with itself. So every particle of matter is associated with a corresponding wave. This is according to Louis de Broglie, and it's called the de Broglie wavelength, as a particle's wavelength is related to its momentum. All right? So if we consider an electron moving at a certain velocity, then the wavelength of the electron would be equal to Planck's constant, again, the constant that is used for basically all of quantum mechanics. It's the numerical fitting number. It's one of the fundamental constants of the universe. And so it would be Planck's constant divided by the mass of the electron times the velocity of the electron. So this is different than how we would relate wavelength to frequency for a photon. Because wavelength of the photon, it's good to compare the two because they're similar formulas and it's easy to mix them up. The wavelength of the photon is equal to the speed of light divided by the frequency, but the speed of light is a constant. There's no such constant for the velocity of an electron. An electron can travel at any velocity as long as it's slower than the speed of light. And we haven't talked about why that is, but we will actually show in special relativity that it takes an infinite amount of energy to take anything with mass up to the speed of light. Thus, nothing with mass, including very little mass like an electron, can travel at the speed of light. But anyway, the relationship between the wavelength of a photon and the frequency would be wavelength photon equals c divided by the frequency of the photon. Okay? So notice the difference between the two formulas. Okay? The wavelength of the photon doesn't require Planck's constant to relate it to the frequency. But to find the wavelength of an electron, we do need Planck's constant, okay? And we need to know its mass and its velocity, okay? But what is interesting about this wavelength is it can be actually quite short because the masses of an electron and their velocities can be such that we can get wavelengths, electron wavelengths, that are shorter than the electron in visible light, which leads to electron microscopes. Okay? So when we speak of de Broglie waves, we're speaking of the wave nature of what? Okay? Particles. Particles, particles. That's what de Broglie waves are. Like electrons, you can talk about the de Broglie wavelength of neutrons, of even things like alpha particles, which is the nucleus of a helium atom, so 2 neutrons and 2 protons. So really small particles like that. Now, is it possible of larger particles, larger molecules, or more massive exotic particles? Yes, but what ends up happening is the wavelength becomes so small it becomes difficult to measure, okay? Because if you see here, the wavelength starts to become really small because Planck's constant is 6.626 times 10 to the negative 34 joule seconds. So if you have some macroscopic object that maybe weighs a kilogram and is moving at some average speed of a couple meters per second, say 1 meter per second, then now your wavelength is 6.626 times 10 to the negative 34 meters. Well, that is 20 orders of magnitude smaller than the atomic nucleus. It's so small that it's beyond anything that we've ever approached measuring. So it'd be absolutely unmeasurable based on any modern physics. All right. So here we see the interference patterns of beams of light, okay? And we can also create interference patterns with electrons. So electron microscopes use that wave nature of electrons to create images similar to the image of a mosquito shown here. Now, one thing I remember always asking is, okay, well, that's great. We can show that electrons have wave properties. They can then behave like a wave. They can be used then to image things based on wave properties like interference and reflection, okay? So basically diffraction, reflection, and interference, superposition of waves, like everything that we use for, either using ultrasonic sounds to discern the shape and positions of things with sound waves, or traditionally, of course, using visible light to see the world around us. Okay, so that makes sense that the wave nature of electrons can allow for visualization. But why electrons? There are certainly shorter waves than visible light that are light. Why not, say, use X-rays for visualizing things? We use X-rays for visualizing dense things inside of soft tissue. We can, see the bones with X-rays. Here's the reason. If you want to use an electron wave, that is, say, the right wavelength for finding very small details on an insect, maybe you want an electron wave that is about the size of an atomic nucleus. So 10 to the negative 10 meters, okay? So first of all, that's going to be much smaller than visible light, because visible light is on the order of 10 to the negative 7, all right? So wavelength visible light is on the order of 10 to the negative 7 meters. So we're looking at something that's 1,000 times smaller than visible light, okay? So that's, you can't do it with visible light, see something that is this small, but you can do it with electrons, okay? So you can visualize things that are on that scale, and that's kind of the upper limit. Maybe 10 to the negative 9 is a little bit less ambitious, right? But there you go, okay? You can create an electron wave that is 10 to the negative 10 meters. Okay, great, visualization. But still, as I was just saying, why not just use a light wave? X-rays are 10 to the negative 10 meters because of the energy. If you calculate how much energy an X-ray has that has a wavelength of 10 to the negative 10 meters, you get a huge amount of energy. That's how X-rays can travel through soft tissue. All right? If you try to use an X-ray to image our little fly body here, it would break it apart. Okay? The time it takes to expose enough X-rays to actually resolve an image, you would dissolve the sample in many cases, or in the least significantly damage it. It's just, we're talking about two fragile things at this scale. There's really no way to do it without damaging the sample. Now there are exceptions, certain really strong materials that come in small pieces, and you could use X-rays. Okay, certain minerals, mineral structures, but many soft examples you can't. But if you look at the electron wavelength and the energy of an electron that has a wavelength of 10 to the negative 10 meters, much less than the X-ray. Now you see the utility of it. Now you see why X-ray wave properties are so useful, because it's lower energy, short wavelength visualization. All right, so I hinted at this a minute ago, this idea of uncertainty. Because fundamentally, if a photon can interfere with itself, and now we know if an electron as a wave can interfere with itself, that means there must be a fundamental uncertainty. The position can't be known because we don't know where it's going to land on the screen, right? It's going to behave as if it's a wave, as if it's like predicting what all its other particles are going to do. Almost this idea, what sometimes was called, rightfully called, quantum entanglement, almost like all these quantum particles are communicating without even communicating. They'll build up information, but only once they have a chance to interact with each other. But even more than that, even more basic than quantum entanglement, is just that uncertainty, that idea that we don't know where the photon's going to arrive, but there's likelihoods where it's going to arrive on the screen. All right, so that leads to something called Heisenberg's uncertainty principle, which is one of the big ideas behind quantum mechanics. And it's so interesting that just taking something and quantizing it and then saying, oh, but it's also a wave, thus getting duality, leads to uncertainty. It's just this cascade of consequences with these physics theorems, that you have one idea, like Einstein's idea. What if light always travels at the same speed no matter your reference frame? And then that leads to this incredible slew of consequences that then lead to this theory that changes our understanding of space and time. Likewise here, we have what if light is a particle? Okay, then it must have built-in uncertainty. Amazing, right? So the uncertainty principle states that the act of observing something as tiny as an electron probes the electron, and in so doing produces a considerable uncertainty in either its position or its motion. It's the German physicist Werner Heisenberg called this the uncertainty principle. So often it's called Heisenberg's uncertainty. Okay? When the uncertainties in measurements of momentum, so that's just mass times velocity, and position for a particle are multiplied together, the product must be equal to or greater than Planck's constant divided by 2 pi, okay? Which is represented by h bar. So h bar is just Planck's constant, 6.626 times 10 to the negative 34 joule seconds divided by 2 pi, okay? Oh, excuse me, divided by 2 pi, okay? That's h bar. Okay, so it sets the uncertainty. So that means if you know, so delta P would be your uncertainty basically in velocity, okay? Because you might know the mass exactly. Okay? In case of the electron, you would know the mass. You might, because again, momentum is just mass times velocity. So if you know the velocity very well, you know exactly how fast that electron is traveling, then you need to know less and less about its position. Because if you make delta P really small, then delta X has to be appropriately large to keep this inequality. Now, it doesn't have to be that large, because after all, this is a small value, but it does have to be there. And it becomes important. It becomes so that the uncertainty matters in a lot of experiments that are on the wavelength of your particle. All right? So just to elaborate on the terminology here, the delta is the uncertainty in the measurement. So delta P is the uncertainty in the measurement of P, momentum. And delta X is the uncertainty in position. The product of uncertainties must be equal to or greater than the size of h bar. So if one is small, the other one has to be larger to compensate. It's like a scale. Okay? So it also applies to the uncertainty measurements of time and energy. So in the uncertainty knowledge of energy, delta E, and the duration taken to measure that energy, the delta T, the delta time, are related by the expression delta E, uncertainty in energy, multiplied by uncertainty in time, always has to be greater than or equal to h bar. Okay, so same idea as the momentum and position. Okay, so those are your two uncertainty statements. Okay, they're derived from the same background. So Heisenberg's uncertainty principle applies only to quantum mechanics, because it just wouldn't be important on the macroscopic scale. It becomes completely unmeasurable. Okay. So to which of these does Heisenberg's uncertainty principle apply? Measuring room temperature with a thermometer, momentum distances of a high-speed bullet, a public opinion survey, or none? None. None of those are microscopic on the scale of basically atomic particles, right? None, not even close. Even the smallest one, the high-speed bullet, and I guess I just think that because it could be kind of like you start to get kind of like higher in physics, right? It's not like everyday speeds, but it's still not even close enough. Okay, the bullet is way too massive. So this leads to our final idea here, complementarity. So complementarity is wholeness that often means accepting alternate explanations for the natural phenomenon. Opposite ideas can complement one another, like it be both a wave and a particle. Bohr chose the yin-yang diagram to illustrate complementarity. This idea that you can have opposites as a way for humans to understand these ideas that are so foreign to us. Okay? All right, well, that brings an end to our first discussion into quantum mechanics and a bridge between chapters, because this is the last chapter that will be covered in the next exam, but it is not the last chapter on quantum mechanics, because we're going to get into the atom and continue some of these ideas there. But I hope our last few chapters all about light has reached a good conclusion here discussing light as a particle. Thank you so much for watching. I hope this lecture has been interesting and informative.